Welcome back, everybody. We're in section 2.3, your third section of calculus. I'm looking forward to this. Hopefully, I'm getting to more of you now than just 2 or 3 people. So this particular section is called continuity at a point. So we already know about some discontinuities. We talked about how we can find our holes in our graphs and how we have asymptotes. Okay, and so now what this one's going to do is going to define for us how do we really know, okay, that a graph is continuous. Okay, what are some criteria for there to be there for a graph to be continuous? All right, so in general, what you should already have some idea of what it means to be continuous. Your pre-calculus class, your algebra 2 classes should have already told you that something along the lines of, well, in order to be continuous, if I can draw a line, if I can take my pen, put it down, and go all the way up and down and all the way through without lifting my pencil off the graph, then it's continuous. And that's true. Okay, but now we're concerned about just at a point. Where are things continuous at a point? So I'm going to take a look here. First we're going to do at x equals 3. So I take a look at x equals 3. I go right up here to 3. Does this look like it's continuous? Am I continuous there? It's filled in. Can I take my pencil? Go here. Yep, I can do that. No jumping around. I think it's continuous. So we'll start there. Then let's go and talk about x equals 2. Let's take a look at x equals 2. If I go here to x equals 2, I have to take my pencil off the graph to circle the dot and then come over here. Well, that's no good. So it's not going to be continuous. Alright, so here we have an idea. This is already continuous. Okay, not continue, IOUS, continuous, okay. And then we have to go, well, what about 3.4, 4, 0, and 1? I'm going to leave you to go and figure those out. I'm going to let you figure them out and see what you think, just based off your gut. All right, I'm not going to make you answer all the questions, but I am going to pause the video here and make you think about it for a little bit. All right. All right, there are the answers. Now the question is, okay, did you get them? Do we understand why it's continuous versus not continuous? So let's take a look at 2 and 1 and compare it. What's making those continuous, not continuous, compared to the other ones that are continuous? So when I take a look at this, again, we just got done doing a whole bunch of limit stuff, so my brain is still on limits. So I think when I take a look at 2 and when I take a look at 1, here's what I'm noticing. For starters, let's take a look at 2. What I'm noticing is, does my limit exist there at 2? Well, yes. Okay. The limit as x approaches 2 for that function does exist. And what is that limit? That limit is equal to 1. What's my function value? My function value for 2, so f of 2, what is that equal to? 2. Let's go ahead and take a look at 1. What's my limit as x approaches 1 for my function? If you remember everything about your limits, you should see that that one does not exist because there's a break in the graph. And what's the f value? F value of 1 is equal to 1. Now let's compare that to something like 3. So if I take a look at 3, what is that going to talk about? What is that going to do? So if I take a look at 3 and I start going, well, what's the limit as x approaches 3 of my function? That's equal to 2. right? Because it comes from both sides. What's my function value? That is equal to 2. So what works for 3? What's this? Hopefully, maybe we can see what's going on with 3 other than 2 and 1. And then you have to ask yourself, is that the same thing that's happening there at C, D, and E? Okay, for x is equal to 3.4, x is equal to 4, x is equal to 0. Do those all work the same? I think so. I think that when my limit value is equal to my function value, then my limit, I am continuous. That might be a theorem. Let's find out. Continuity at a point. Any function whose graph can be sketched in one continuous motion, okay, that's one we already know. Without lifting the pencil as an example of a continuous function. Great. That's what you should already know. But let's go here. Look at that. See? Here's your formal definition of continuity at a point. We say a function y equals f of x is continuous at an interior point C of its domain if the limit is equal to the function value. That's exciting. Isn't that what we just found out? That's what we kind of just should have come in our head. So what this is saying is that for continuity at a point, the limit value has got to equal the function value. That is what it means to be continuous at a point. Now, when they talk about endpoints, these are very specific about endpoints, if it's continuous at the endpoint or not continuous at the endpoint. Okay? Very specific. Okay? What it's saying here is that if the limit for a right endpoint, okay, B, as the limit comes from the left of B, is equal to the function value. That makes sense. It's right over here, right over here. They kind of show you that. This is the big one because this is what you're mostly going to have to do. In fact, okay, this is so huge that you need to know this. In fact, the AP people are more specific. They want you to check off 3 little things. Okay? And let's see here if I've got room for it. I think it's on the next slide. I got room for it. Yeah. So here are the 3 things that you need to check off for continuity at a point. Okay. First thing is, let's put a little checkbox. First thing you gotta check, does f of c, is it defined? Okay. Next little check mark. I'm gonna go a different color because why? I like different colors. Does the limit as you approach that C, does it exist? Oops. Does it exist? It exists. Okay. The next part is, does that limit value as x approach C of my function equal my function value? You can't just hop to this. You have to actually show these 3 steps. All right? So that's what I want to do real quick here for this one. And if you notice, this particular function, our step function, okay, is not defined, okay, is not continuous, excuse me, is not continuous at each of my integers here. Okay, it jumps. It's not continuous. But if I choose a point, let's say at 2.5 here, okay, and I want to see if it's continuous at that point. So you would go ahead and do your check marks. First check, does f of 2.5, is it defined? Well, is f of 2.5 defined? You betcha. Okay, f of 2.5 is equal to 2. That's defined. Boom, check. Does the limit of f of x exist as x approaches c? So as x approaches c, so this is as x approaches 2.5. What is the limit as x approach 2.5 of my function? Hopefully, again, you see that as being 2. And then the last thing you have to say is, or just show, is that the limit as x approaches 2.5 of my function is equal to f of 2.5. Now I know it looks obvious up here, right? This looks obvious that this is going to be equal, but you do need to say it. So if you're asked to find is it continuous at a point, I need to see these 3 steps. All right? Put a star on it, you know, muy importante. Very important. All right? Here we go. Next. So now we've looked at continuous at a point, okay, continuity at a point, we have to describe some of our discontinuities. All right? So if this one here, it's not very clear, but this one here, there is no hole, it's just a straight line that goes all the way across. This one's continuous. All right? This one has a hole here. I know it's very hard to see, but there's a hole there. And this one is what's called a removable discontinuity. This one here as well has a hole here, and there's a dot up here. This one is also called a removable discontinuity. Holes are another way of saying removable discontinuity. A hole is a removable discontinuity. Why is it a removable discontinuity? Because if I redefine my function, if I say f of x is no longer just this with a hole in it, if I redefine it as a piecewise function and I use something to plug up the hole, if I say, well, f of 0 is equal to 1. If I say when x is equal to 0, my function is equal to 1. That's then no longer my discontinuity is there, which is why it's removable. Okay? The other types of discontinuities that you have, this one here, when you have a function, again, you can't see it too well, but that's what the function is. It jumps, so this is called a jump discontinuity. One where you have an asymptote. Okay, there's an asymptote, right? An asymptote is also called an infinite discontinuity. And finally, there you don't see this very often, but if you have sine of 1 over x, the function looks completely crazy. You should graph it in your calculator if you got some time. And what's really fun to do is zoom in on it. And as you're zooming in, it feels like you're going through a time warp because of the way that it keeps zooming in, zooming in, zooming in. So what this is called is it never fluctuates. Is it called an oscillating discontinuity? Okay. So you need to be able to recognize it when you say look at it. You need to be able to say, well, that's a jump discontinuity. Okay, boom, that's an infinite discontinuity. Oh, the hole, that means there's a removable discontinuity. You need to be able to identify these by looking at them. All right? So if you need to say that a function is continuous on an interval, you need to be able to say that it's continuous at every point on the interval. Now, that's kind of hard to prove, okay? But the idea is that if you're told that a function is continuous, then it's continuous everywhere, and you don't have to go and try and prove it, okay? Which becomes handy again in the future. A continuous function is one that is continuous at every point in its domain. Now, this part right here, this part is where it gets to be tricky because each book is a little bit different. And the reason why I say that is this problem here. Okay, our book defines that a function is continuous at every part of its domain. So if you notice here, the domain for 1 over x is all reals, okay, except when x, okay, cannot equal 0. That's the domain. So when you sit down there and say, well, shoot, is it continuous everywhere else? Is it continuous on every other point? Sure, just except at 0. So this, even though it looks like, yes, it's an asymptote, yes, it has a infinite discontinuity, it is still considered a continuous function because it's continuous on its domain. Because it however, it has a point of discontinuity. So is continuous function because it's continuous at every point of its domain. However, it has a point of discontinuity because it is not defined there. Okay, so each book is different. Our book says it this way. Good news is that AP doesn't try to trick you or try to get you which book did you read, so you won't have to be messed with it with that question. All right, so here we go. I just want to show you that. So here's your homework. All right, part 1. All right, a big long list of ones. You're going to have to find some discontinuities, okay, identify them. If you have any problems, again, email me. Please take a moment to summarize what you have learned, and so that way I can check to make sure everyone's understanding it the way it's I've been presenting it. All right, see you guys next time.